Okay, in this section we're going to talk about some details of matrix multiplication. And in particular, we're going to relate matrix multiplication to row operations. If you remember, row operations involved switching rows or adding a multiple of one row to another row, or there's another one that slips my mind for the moment. Oh, just multiplying a row by a number. We're going to relate all of these operations to multiplication by matrices. All right, so notice how when you multiply, rows and columns combine. The row of the first matrix combines with a column of the second matrix to obtain a single entry whose row index agrees with the first row and whose column index agrees with the second row, with a column in the second matrix. Okay, so that's what he says here. The ij entry is the dot product or inner product of row I in the left matrix with column j in the right one. We can view this as the left matrix acting by multiplying its rows into the columns of the right matrix. Or we could see it as the right matrix using its columns to act on the left matrice's rows. Okay. Now, a matrix with all zeros except for a 1 in the ijth entry is called a ij unit matrix. Okay, so for instance, if you have a 2×3 matrix size, there are 6 possible unit matrices. There could be a 1 in this entry, or a 1 just in this entry, and so on. Okay. Now, if you do this, what's going to happen? If you have this unit matrix, when you multiply this row by any of these columns, you'll get a 0. So what does that mean? That means that the corresponding row here that corresponds to row 1 here is also going to be all zeros. Now, here we have, if we multiply the second row, we're just going to pull out the first row from here. Why the first row? Because when I multiply 1, 0, 0 times each one of these columns separately, I'm only going to pull out the first entry in each column. Okay, this is a mistake. It shouldn't be here. Okay. On the other hand, if I have a unit matrix on the right, we know that these two columns, the third column and the second column, are all zeros. So that implies that the second and third column of the result will also be all zeros. When I multiply this column by the matrix here, well, think about the first row here. If I multiply this first row times this column, I get 3 times 0 plus 4 times 1 gives me a 4. And I get 6 times 0 plus 5 times 1 gives me a 5. I just get the 4, 5. So what is the 4, 5? The 4, 5 is, in fact, the second column of the first matrix. Okay, so why 2? Because it was the second entry in the column. You can verify for yourself that if the 1 had been in this place, it would have put the first column here, 3, 6, into the first column over here. Okay, so it copies column 2 of the first matrix into column 1. Why does it copy column 2 into column 1? Because this is column 1, and the 1 here is the second entry of column 1. Now, if we rescale the unit matrix, we'll just multiply all of the entries of the result by the scale. So we multiplied unit matrix here by 3. This result is also multiplied by 3 compared to this result. Lemma. In a product of two matrices, G and H, the columns of GH are formed by taking G times the columns of H. Okay, so we've done before multiplication of matrices by column vectors. So this is a nice idea, that if I want to multiply two matrices, I can multiply column by column in the second matrix. The first column of the result is the matrix on the left G times the first column of the matrix on the right. The second column of the result is the matrix G times the second column on the right, and so on. Similarly, the rows of the product GH are formed by taking the rows of G times H. Now this is a little bit less familiar, but it's similar. I have this matrix H, which is the matrix on the right, and I multiply the rows one at a time with that matrix H. If I multiply this row times H, I'm going to get this row times the first column, this row times the second column, this row times the third column, etc. It turns out that when I finish that process, that's just the same thing as multiplying this row by the entire matrix H. Okay? Okay. So you can prove this in general using complicated index notation. Let's just do it for 2 by 2, and you can see how this works. Okay. So I have my matrix G, which is a 2 by 2 matrix. The first index indicates the row, second index indicates the column. Same with my second matrix H. Okay. If I just multiply these together, I can take the product here of G11, G12 times H and evaluate that, and I just work it out, and you can recognize this as the product of G times H. Okay. All right. So you can work it out both by doing straight multiplication and by multiplying each row by the corresponding matrix H. And you can do the others similarly. Some other important definitions: the main diagonal or principal diagonal, or sometimes just diagonal, of a square matrix goes from the upper left to the lower right. Okay, so here we have ones on the diagonal, or you could say ones on the main diagonal. An identity matrix is a matrix that has ones on the main diagonal and zeros everywhere else. If you take the product of an identity matrix with any other matrix, it returns that matrix. And this is true both on the left side or on the right side. Now, of course, the identity matrix must have the right dimension in order to multiply, but as long as the identity matrix has the right dimension, then when it multiplies another matrix, it will give that same matrix. And you can verify these multiplications yourself. Okay. A diagonal matrix is square and has zeros off the main diagonal. Okay, so an identity matrix is a special case of a diagonal matrix. Multiplication from the left by a diagonal matrix rescales the rows. Okay. Why is that? Because here I know that the first row of the result is the first row of the matrix on the left times this matrix. If I multiply this row by 2, I'm going to multiply the first row here by 2. Okay. Similarly with the second. You can just work out the details of this multiplication and you'll see. If I multiply this row times this matrix here, it's going to pick out 3 times the second row here. On the other hand, you know that when you multiply on the right, you're picking out columns. If I multiply 2, 0 here times here, I know since this is the first entry of the first column, the result is going to go in the first column, and it's going to pick out the first column of this left-hand matrix, giving me 3 times 2 is 6, 3 times minus 1. I'm sorry, 2 times 3 is 6, 2 times minus 1 is minus 2. For the second column, it's 3 times the second column here, 3 times 2 is 6, 3 times 5 is 15. Another definition, a permutation matrix is square and is all zeros except for a single one in each row and each column. So each row has a unique 1 and each column has a unique 1. So it's kind of like the identity matrix rearranged. If you have a 3 by 3 permutation matrix, it has 3 ones in it, and you have to place one row in each one in each row and each column. Now if I multiply by a permutation on the left, it will swap rows. Okay, these two, if you notice, this permutation matrix is the same as the identity matrix with the first two rows swapped. And you can work out this multiplication. If you multiply this on the left by another matrix, it will swap those same two rows of this matrix. Similarly here, this permutation matrix is the identity matrix with these two columns swapped. If I multiply this matrix on the right by this matrix, it's going to swap these two columns of the original matrix. Right? Here I had 147 in the first column. Now 147 is in the second column. Here I had 258 in the second. Now it's 258 in the first column. The elementary reduction matrices, or just elementary matrices, result from applying a one Gaussian operation to an identity matrix. Okay? So if I multiply a single row of the identity matrix by k, then that's going to give me an elementary matrix of type M. Okay? And I have to specify the subscript I because this will be different for each different row I. If I apply a row exchange to the identity matrix, then I call that an elementary matrix of type P. If I add a multiple of one row to another row, I call this an elementary matrix of type C. Okay. Here's some 2x2 examples. M23, what's that going to do? It's going to multiply the second row by 3. What does P12 mean? P12 means I swap rows 1 and rows 2. C12 of minus 3 means what? It means I multiply minus 3 times the first row plus the second row. Okay. And in all these cases, I'm starting with the identity. So if I start with the identity here, and I take minus 3 times the first row plus the second row, well, the first row remains the same, so I have 1, 0 here. If I take minus 3 times the first row as 1, is minus 3 times 1 gives me the minus 3. And then for the second one, minus 3 times 0 plus the second row gives me a 1, so that gives me this entry here. For some 3x3 examples, similarly, you can work this out. P23 means you exchange rows 2 and 3 of the identity matrix, which you can see here is the exchange. C23 minus 4 means I take the second row of the identity matrix, multiply it by minus 4, and add it to the third row. And there's a mistake here. This should be a 1 here. Okay? Now, suppose I multiply on the left by M2 of 1/2. This is the elementary matrix that corresponds to multiplication of the second row by 1/2. Now remember, we got M2 of 1/2 by applying multiplication of the second row by 1/2 to the identity matrix. Here it is right here. Take the second row of the identity matrix, multiply it by 1/2, you get this. Now the magical thing is that if I now multiply this matrix by another matrix, that will exactly perform the same elementary row operation on this right-hand matrix. Right? I mentioned that this elementary row operation is 1/2 times the second row. And if you perform this operation, you'll see that the second row here is exactly 1/2 times this second row. Okay. Now C13 of minus 2, that's minus 2 times the first row plus the third row applied to the identity. So we can see that's what we have here. This last row here is the same as minus 2 times the first row plus the third row. Now if I multiply this elementary matrix on the right by any other matrix, the result will be the same row operation performed on this matrix. Okay. If you take minus 2 times the first row plus the third row, you'll get minus 2 plus 2 is 0, which is correct. Minus 2 times 3 plus 1 is minus 5, which is correct. And minus 2 times 0 plus 1, which is 1, which is correct. Okay. So we have a way to perform row operations by means of matrix multiplication. Okay, matrix multiplication can do Gaussian reduction. Well, since we've seen that we can do row operations by matrix multiplication, then all we have to do row reduction is multiply successively on the left by the different matrices corresponding to the different row operations. Okay, I wouldn't say it's so clear, but I think after the explanation, hopefully you can understand that. So for any matrix H, there are elementary reduction matrices R1 through RR, such that RR times RR minus 1 times ... times R1 times H is a reduced echelon form. Now remember, when you apply the row operation to a matrix, you multiply it on the left. So R1 corresponds to the first row operation that would be applied to the matrix H. After that's done, you'd apply R2 to the result, and so on. RR would be the last row operation applied to the matrix. And we know that we can choose a sequence of elementary row operations to change H to reduced echelon form. So we can just multiply by the corresponding elementary matrices to perform the same reduction. Okay, we can bring the augmented matrix to echelon form with matrix multiplication. Okay, we first perform this row operation, minus 2 row 1 plus row 2, through left multiplication. Okay, so if we do minus 2 times row 1 plus row 2, that's going to give us a 0 here, right? If you do this matrix multiplication, you'll find that that actually accomplishes the row operation that we wanted to. Now, the next row operation you probably want to do is switch these two rows. Okay, and that's exactly what he does. This is the elementary matrix corresponding to row swap of 2 and 3. And that performs the row swap. You can see these rows are swapped from here. Now, what's the next thing you'd want to do? Probably want to multiply this by minus 5, divide this by minus 5, divide this by 3. Okay. Well, actually, this is in echelon form, not reduced echelon form. But we have gotten this into echelon form using this sequence of row operations. Using this sequence, and these row operations correspond to matrix multiplications. Okay, let's stop here.